you have to go through this firstly by website. If you lost an electrical diploma.2013.social.com, and then this will be the material science. So if I click the material science, so you can see that this download as a file. You open. So then, in this case, we have to take the basic theory, advanced theory 1, 2. So firstly, we take up the basic theory. So we take up the basic theory, and then we open at this file. After you open the file, there will be this file here. So there will be a solid. We're talking about last week. We're talking about the solid. We're talking about the gas model. So in this case, there are two kinds of gas, ideal and the perfect gas. So the perfect gas is the ideal gas law. In this case, the meaning of the perfect gas means the gas must follow the equation PV equal to nRT. So that equation is a gas equation. So P is the pressure, V is the volume, and this will be the number, R is the constant. Universal constant, and this is a number. So this must follow any gas follow this equation. That will be the perfect gas law. This is we can also classify the gas. Some gas are perfect, some gas are imperfect. Depending on the molecular structure and the interaction force between the gas molecule, the gas can be classified the perfect or the non-perfect gas. The perfect gas we can define. It follows the PV equal to nRT, this equation. So P is the pressure, the V is the volume, N is the number of the molecule, and I is the constant, T is the temperature. So the gas follows this equation, PV equal to nRT. This is we call it a perfect gas. So P is the pressure, V volume, and then also the R is the universal constant 8.314 joule per molecule per K. 8.314. So then we use a perfect gas we can write down the equation. So in this case we also see the equation here. So this equation is a perfect gas law. Ideal gas equation, we get ideal gas with real gas with compressibility is set 1, then we use the ideal gas equation. So this is the meaning of the ideal gas. So ideal gas is the compressibility pressure, say it is set to 1, then we use ideal gas. Ideal gas. So there will be the some gas are the real gas. Real gas means that it equals the gas property. For example, when we are heat the water, so the some water they only contain the moisture. When the water contain the moisture, this is not yet the real gas. So real gas means it must follow the equation PV equal to nRT equation. It must be followed. So this means the perfect gas. So then we describe the ideal and the perfect gas model. So the equation PV equal to nRT is the status for the ideal or the perfect gas. So ideal gas law applies without restriction on the specific heat. The compressibility factor Z is the set 1. So this is the meaning of the perfect gas. Now we have to describe which is the real gas effect. Describe the real gas effect. When the real gas effect means this is the compressibility factor. Gas can be compressed. If the gas cannot be compressed, this is not gas. Because of all So we also have to describe about the real gas effect. The real gas effect means some gas are not real gas, they cannot be compressed. So that to become the real gas, that will be the compressibility effect. So this means gas must be the compressed. So compressibility is a measure by the compressibility factor. The Z should be the 1. So if the Z compressibility factor say 1, that will be the real gas. And also they must have the heat capacity. So this is the heat capacity. So real gas means they must have the compressed factor. You can change the volume. Also we must have the heat capacity, specific heat capacity. Also we also have the non-equilibrium thermodynamic aspect. So gas must be also the transfer the heat. Also molecular dissociation. So gas molecule can be dissociated at the starting temperature and the pressure. So this is the important aspect of the real gas effect. For the definition of the real gas effect, so there can be the compressibility effect. This means that whether gas can be compressed. When you compress the gas must be compressed and the volume will be smaller. When you release the force, gas will be expand. So this compressibility factor Z is allowed to vary from 1 to 0. 1 means that this is the original volume. So varies 2, 3, 4 means that expansion, and 0.5, 0.3, 0.2 means that is compressing. So this is the gas can be compressed. Whether the gas is a real gas or the other imperfect gas, this means the gas, if the gas is a real gas, it can have the compressibility effect. Also, it also has a variable heat capacity. So the specific heat value R must be vary with the temperature. And also between the gas molecule, there will be the force between the gas molecule. There will be also we call the Van der Waals force. So they also related to the compressibility and can substitute the other equation of the state. And also the non-equilibrium thermodynamic effect. So this when the gas is provide, so depending on the temperature, the heat will be transferred. So the gas normally not equilibrium. So in this case, the gas will be expanding, so the heat can be the loss. So that is a non-equilibrium nature. The issue with the molecular dissociation and the elementary reaction with the variable composition. This means the gas molecule can be dissociated depending on the temperature and pressure. They can be combined, they can be separated. So those are the characteristics of the gas. So that is the real gas and the imaginary gas. So this is you see the gas. When we are gas coming out, so there will be this we see the real gas. So they must have the compressibility effect. Real gas must have the compressibility. They must have the variable heat capacity. So they can be compressed. So this the compression factors are allowed to vary from the 1. They must have the specific heat capacity. The specific heat vary with the temperature, and also the force between the gas. They also have to have force between the gas and non-equilibrium thermodynamic effect. So when you provide the thermodynamic means this gas are also changing with the volume. Also all the heat transition are also changing. And the association of and the elementary reaction with the variable composition. So those gas are all the equipment. They must have the appropriate molecule. Depending on the temperature and pressure, gas molecules they are changing. They are combining. They are dissociation. Those are included in the gas properties. Okay, the next one with the Avogadro law. So all the gas laws can be the Boyle law. Boyle law will be the temperature and the pressure. So all the temperature and pressure, the multiplication of the temperature and the pressure can be constant. So this is the Boyle law. P into V is equal to constant. So this is for the Boyle law. In the meantime, loss of the volume. So this way is loss of the volume is the Charles law. The Charles law also you can use the Vn by temperature as a constant. So this is for the Charles law. So volume divided by temperature is a constant. So we have the Charles law. The next one is the Avogadro law. Avogadro law. So in this case, there was a question. So why is it write the Avogadro law? Question 50. Write the Avogadro law. The multiple gas. When we use the multiple gas, so this is a Avogadro's define. Describe the gas in the container which pressure and the temperature are constant. So the gas in the temperature, Avogadro law, they describe a gas in the container in which pressure and temperature are constant. So in this case, V by and it's a constant. So this is for the Avogadro law. So Avogadro's constant represents, so we also have to know about the constant. This is the pressure and the temperature. So it's constant, so this constant value can be determined. So Avogadro's constant represents the number of atoms found in the 12 grams of the elementary carbon. So it can contain a 22.4 liter. So this is for the molar volume. So the molar volume can be driven from the Avogadro law. Avogadro law states the equal volume of the pure gases contain the same number of the particles. So this means when there's equal volumes are equal, they also include the same number of the particles. So this is for the Avogadro law. So we have to measure the specific number of the gas. So how many for example, 12 grams of the elements are carbon, they measure how many atoms will be required to take with the specific volume number of the gas particles. They can measure the specific number of the gas particles. So in this case, for the same volume, they also get the same number of the particles. So we can also write down the equation. So that will be the Avogadro's constant. So Avogadro constant can be written, the equation. So V by N is the constant. This is also the RT by P, also the constant law. This is for the constant equation. V by N equal to RT by P. So this is the constant law. So this is for the Avogadro's law. Avogadro law means when you see the pure volume, equal volume of the pure gases, they contain the same number of the particles. This is Avogadro law. Okay, Jordan law is they are published in 1801. This means the law of the partial pressure. So that way the subject gases are in the subject container. That way this is the gas 1. Here gas 2. Here gas 3. So gas 1 got the pressure P1. Gas 2 got the pressure P2, and gas 3 got the pressure P3. So the whole container, total pressure is a PT. Total pressure is PT is equal to gas 1 pressure P1 plus gas 2 pressure P2 plus gas 3 pressure P3. This is all the container, we are combining as multiple gases. So total pressure is equal to the summation of the individual pressure. So pressure total is equal to pressure 1 plus pressure 2 plus pressure 3. This is the Jordan law. Jordan law means the pressure of the mixture of the gas is equal to the sum of the pressure of all of the constituted gas below. So this is the Jordan law. Okay, this is we can talk about Avogadro law and the Jordan law. Jordan law means the pressure of the mixture of the gases is equal to the sum of the pressure of all the constituents of gas below. So this is the pressure total is equal to the pressure 1 plus pressure 2 plus to the pressure M. So there are 3 gas. We can combine all pressure P1, P2, P3. 2 gas P1 and P2. So this is all the gas of pressure is equal to pressure 1 plus pressure 2 plus pressure M. So we can write down the equation. Then we do this Jordan law. After that, we also know about this Reynolds number. Reynolds number means we have to design this dimensionless number. How much the inertial force, the ratio of the inertial force to viscous force. So this is the Reynolds number. Reynolds number means when you are all the gas got the inertia. So those inertia And when the gas molecules they are combined each other, they are attracting each other. This is the viscosity. So the inertial force and the viscosity force, the ratio is the Reynolds number. So depending on the Reynolds number, some gas can be easily disassociated. Some gas can be difficult to disassociate. So the initial force, ratio of the initial force to viscosity of the force is the Reynolds number. Reynolds number will be the Reynolds number is the ratio of the initial force Vs multiplied rho to the viscosity of force mu by L. So it can be used to characterize the flow. This means that all the gas got the molecule got the inertia. So those inertia and their viscosities are also related. So that depending on the Reynolds number, some gas are easy to flow, some gas are difficult to flow. So this means that the gas probability, flow probability can be described by in terms of the Reynolds number. So out of that also gets called the viscosity. So viscosity means the physical properties to measure out the flow, how well the adjacent molecules stick to the one another. So this is the viscosity. So those are the gas molecules in the diagram you can see. So those are molecules they are attaching each other. So when the viscosity high, difficult to separate the molecule. When the viscosity low, easier to separate the molecule. So therefore the viscosity is the measure of how well the adjacent molecule stick to the one another. So a solid can withstand the shearing force due to the strength of the sticky intermolecular forces. A fluid will continuously deform when subject to the similar load. Now, while the gas has a lower value of viscosity than the liquid, it stays the observability property. So this is the viscosity is a physical property. The measure of how well adjacent molecules stick to one another. This is the viscosity. Okay, the next one we use thermodynamics. When the gas you compress the energy, so the energy can be transferred from one place to another place. So that we use thermodynamics. So energy heat can be flow from the gas layer. When the energy transfer ceases from the system, this condition is referred to as the thermodynamic equilibrium. So this condition implies the system and the surrounding are at the same temperature, so that the heat no longer transfers between them. So in this case, there will be the thermodynamic equilibrium. Thermodynamic equilibrium means all the heat transfer will be stopped, and the system and all surrounding are at the same temperature, so that the heat no longer transfer between them. So it also implies that the external force are the balance. External force are balance means the heat also the transfer is depending on the temperature. When the temperature is different, in this case the heat will be transferred from the hotter particle to the cooler particle. So when the heat transfer is stopped, there will be the thermodynamic equilibrium. And also depending on the external influence. So this means that all the external influence also affect the heat flow. For example, the pressure and the temperature changes, they can also affect the heat flow. So that all external influence must be stopped to achieve the thermodynamic equilibrium. When the energy transfer ceases from a system, this condition is referred to as the thermodynamic equilibrium. All the external force must be balanced. Also, all the chemical reaction within the system are also the balance. So all the reaction force, the force are the balance. All external force are balanced, and all chemical reaction within the system are balanced. Then we achieve the thermodynamic equilibrium. So until this week, I'm talking about the perfect gas. Perfect gas is it can follow the equation. P equal to nRT is this equation. So P is the pressure, P volume, and the number of molecules are the constant. So T is the temperature. Ideal gas is a simplified gas. Real gas with the compressibility is set to 1. So the set to 1 means this gas will not be the expanding or will not be the contracting. So the ideal gas and the perfect gas model, the equation PV equal to nRT is stated for the ideal gas or the perfect gas. The ideal gas law implies without restriction on the specific heat, the compressibility factor Z is set to 1. And describe the gas effect means the compressibility effect and variable heat capacity, van der Waals force, non-equilibrium thermodynamic effect, issue with the molecules association, and the element reaction with the variable composition. So there are the gas laws are three gas laws. Y law is equal to the PV equal to constant, Char law is the PY is a constant. Avogadro law means equal volume the pure gases contain the same number of the particles. And Dada law means that when you are combining the multiple gases, so their pressure is equal to sum of the individual pressure. The pressure of the mixture of the gas is equal to the sum of the pressure of all the constitution gases alone. So the pressure total is equal to pressure 1 plus pressure 2 up to the pressure m. The Reynolds number is the ratio of the inertial force Vs rho to the viscosity of the force mu by L. So it can be characterized the flow. So depending on the Reynolds number, the flow rate also depending on. The viscosity is a physical property, is a measure of the how well the adjacent molecules stick to one another. So viscosity high, the molecules are stick, their force is strong. The thermodynamic equilibrium means that when the energy transfer is strong in the system, this condition is referred to as the thermodynamic equilibrium. It also implies that external forces are balanced and all the chemical reactions within the system are balanced. So those are the gas properties. So you see this at this my site, and by clicking this on material science, so you can download the file. This is the folder here. Then we will here. There will be the dielectric strength. This folder. So go to here. This my site, and you click the material science. So you can call it this folder. So there will be the folder here. Basic theory, advanced theory. But you have to click the basic theory. By clicking the basic theory, you can see that this zip file. So this one inside, there will be the dielectric strength and the material science. So we're talking about the dielectric strength. So dielectric strength is here the insulation of material. So this is for the dielectric strength because the meaning of the insulating material maximum dielectric field strength that can withstand the intrinsically without breaking down, without experiencing the failure of the insulating properties. The point given a configuration dielectric material dielectric strengths are that produce a breakdown. So maximum dielectric strength and the dielectric material can withstand it without breakdown. So this means that they have got the property to withstand the electrical current flow or without breaking down. So this is the dielectric strength. Yes. The transmission lines are usually called the transmission line tower. So this is the tower. Here we hang the insulator. So those are insulator. And here with the cable. So that we insulators are protecting the electrical current flowing cable not to touch to the tower. So we utilize the insulator. So this is the transmission line insulation. So this is the transmission line for insulator. The pin and the suspensions are insulator string to prevent the electrical current flow in the conductor not to reach the tower frame. So this is the transmission line insulator definition. Breakdown. Normally the insulation has the properties of the dielectric strength, but when the electrical current is too much, the insulation can be broken down. So the free strength and with the breakdown order depend on the respective geometry of the dielectric insulator and electrode with which the fee is applied. When the fee is applied, in this case, those insulation layer can no longer prevent the electrical current flow and the insulation will be breaking down. So this is what the dielectric strength is totally breaking down when the force and the field are too high. So this is the definition of the insulation breaking down. So that we also know about the several materials are dielectric strength. So those are the given the materials are dielectric strength. If you got this helium dielectric strength, it should be the 0.15. Air is a dielectric strength of 3. And also the window glass is a 9.8 to 13.8. And silicon white, there will be the 10 to 15. Polyethylene is a 19.7. And also the vegan wax paper they got the dielectric strength. The mica is the highest one. Mica dielectric strength is 118. So this unit we can utilize the dielectric unit. So the dielectric strength unit is a measure in the megavolt per centimeter, volt per centimeter, or the megavolt per meter. So this is the strength of the dielectric strength. We measure the unit, the volt per centimeter or the megavolt per meter. This is the dielectric strength unit. And the last question. So we also need to know about the both times are characteristic of the broken down. So this means that when we are applying this voltage and the time, so then we will insulation will be the broken down. So this broken down diagram is a both time characteristic. To utilize this will be the sphere, and this is another sphere. Then we give the voltage here. The electrical current we give the voltage, we increase the voltage. So here we increase the regulator. We increase the voltage and then we measure the voltage. So when the voltage reaches a starting level, very high level, in this case the electrical current will passing through the one electrode to the another electrode. So then we will that time insulation will be broken down. So that you can also measure the die here. This is the die. Here is the voltage. So you increase the voltage, insulation will not broken down, and when they increase at this level, the devil is a broken down characteristic. So this is insulation broken down. So that time required to broken down, we can plot the graph. So this is the 4 times characteristic. Okay? So we have to make a small hole on the test piece and slowly increase the voltage. And plot the time and the amount of voltage given to the test pieces until it is broken down. So this means that we can see the details of procedure. This is the 4 time characteristics of the testing. So make a small hole in the test piece with the electrode over the hole, slowly increase the voltage until it starts jump the gas and know the voltage. So to determine the test voltage, use a value midway between the test voltage and the calculator using the formula, and then make the sample in the test pieces. In this case, how long will take to the electrical current to pass through. So this is for the both time characteristic and the breaking down. Summarize the two tonight. Then firstly, I'm talking about the viscosity and the gas. So gas can be the perfect gas and the real gas. So we also talk about the gas viscosity and also the Reynolds number and the Avogadro law, Cartan law. Those are the properties of the gas. And together with this one, I also talk about the dielectric strength. Dielectric strength, the ability to withstand electrical current, and dielectric strength can be broken down when the P is too high. And also that we talk about the electric strength and also the transmission lines, insulation property, insulation breakdown procedure, and time characteristic on the breaking down. That's all for tonight. You have to go through this firstly by website. If you lost an electrical diploma.2013.com, and then this will be the material science. So by click the